Welcome to the Diagnostic Clinic. I am incredibly pumped to have you here today. Listen, you are likely preparing for one of the absolute most rigorous, demanding, and ultimately rewarding challenges in your entire academic career, the Cambridge Computer Science Examinations. And whether you're tackling syllabus codes 0417, 0478, 0983, 0984, 2210, or sitting for the advanced 9618, let me tell you, you have come to the exact right place. Today, we are putting on our lab coats, stepping into the role of lead physician, and conducting a full, no-holds-barred diagnostic workup on one of the most notoriously difficult sections of the entire curriculum. We're talking about 9.1 computational thinking skills, specifically focusing on abstraction. Now, let's start by looking at two typical patients in our clinic today. Picture them in your mind. First, we have Alex. Now, Alex is a walking encyclopedia. Alex overloads exam answers with raw, unfiltered computer science facts, writing paragraph after paragraph of memorized textbook definitions, but includes absolutely zero analytical depth. Then, on the other hand, we have Sam. Sam is brilliant, genuinely understands the code, but Sam constantly rushes, completely missing the specific requirements of the command words in the prompt. Both of these students leave the exam hall feeling incredibly confident, and both are absolutely shocked on results day when they see a failing grade. They open up their papers and just see red pen marks everywhere. Today, we are going to diagnose the exact symptoms of these failing answers, look at the precise reasons they get those red marks, and prescribe the ultimate cure to transform them into green check marks and secure those top-tier marks. Get your notes ready, clear your desk, because this explainer is about to change the way you approach every single exam question from here on out.
Okay, let's dive straight into this. A senior Cambridge examiner recently noted, and this is a direct quote by the way, that 9.1 computational thinking skills, and abstraction in particular, is one of the most fundamentally misunderstood areas in the entire computer science syllabus. Let's fix that right now. Why is it so misunderstood? Well, because abstraction isn't just about memorizing a dictionary definition. You can't just write that abstraction is hiding unnecessary details and expect full marks on a rigorous A-level paper. The examiners are looking for something much deeper. They are looking for your ability to apply that concept to incredibly complex, completely unfamiliar scenarios. It's about filtering out the noise to build accurate computational models. It is highly analytical, and guys, it is extremely high stakes. When you misinterpret an abstraction question, you don't just lose one mark, you often lose the thread of the entire multi-part question. Your whole answer unravels. But don't worry, breathe easy. As the lead physician in this clinic, I am going to prescribe the exact cure. We are going to break down the specific assessment objectives that Cambridge uses behind closed doors, and I'll show you exactly how to structure your answers so that the examiner literally has no choice but to award you maximum points.
Here is our rapid-fire roadmap for today's diagnostic clinic. First up, we'll cover core principles. Second, we'll introduce the treatment plan. Third, we're examining the symptoms. And finally, we will wrap up with a clean bill of health.
Part 1. Core Principles. Building the Foundation.
Now, what's really interesting about this is how the theoretical architecture of 9.1 computational thinking rests so heavily on your ability to provide precise definitions, establish crystal-clear causal relationships, and seamlessly integrate your knowledge across the entire syllabus. There is an incredibly stark contrast between an average candidate and a top-performing one. An average candidate, like our student Alex, provides superficial breadth. They cover a whole lot of ground, but with the depth of a puddle. A top-performing candidate provides analytical depth. They exhibit a connected conceptual understanding that is easily transferable to completely unfamiliar contexts. To bridge this massive gap, you need a framework. You need the PEAL framework. P-E-E-L. Point, Evidence, Explanation, Link. Top students structure absolutely every analytical answer this way. You make your point about abstraction, you provide evidence directly from the scenario given in the exam prompt, you provide a detailed explanation of how the computer science theory applies to that evidence, and finally, you link it all back to the specific requirement of the command word. Let's do a quick interactive challenge right now. Imagine a question asks you to evaluate the use of abstraction in a flight simulator. An average student just defines abstraction, but a top student uses PEAL. They make the point that abstraction simplifies the model. Their evidence is the flight simulator environment. Their explanation is that abstracting out specific weather patterns saves crucial processing power, and their link explicitly ties that saved processing power back to the simulator's real-time performance needs. That is the PEAL framework in action. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Part 2. The Treatment Plan. Systematic Methodology.
Okay, this standardized sequence right here is your absolute survival guide for capturing what Cambridge calls method marks. You know, those marks you get just for showing your analytical process. Let's break it down. Step 1. Identify key elements. You completely deconstruct the question. What is the command word? Is it describe, explain, evaluate, or analyze? Step 2. Apply relevant principles. You extract the relevant data and select your analytical framework. Step 3. Execute analysis. This is where the magic actually happens. You do the hard work with clear notation, extracting data from binary representations if required, and building your logical argument piece by piece. Step 4. Verify results. Take a step back. Does your conclusion actually answer the specific question that was asked? And step 5. Present format. You write it all out using correct, highly professional computer science terminology. Let's test this with a data scan challenge. Imagine you're looking at a complex data table representing network traffic in a busy corporate environment. You've got 60 seconds on the clock. An average student panics and tries to read every single raw number in the table. But a top student utilizing step 1, they don't do that. They scan the headers, they look at the axes, and they identify the core trend immediately. They realize, oh, packet loss increases exponentially when the server load hits exactly 80%. Boom, data extracted. When you have barely any time to write a perfect paragraph, you do not panic. You use this 5-step sequence combined with our PLAL framework to systematically build a bulletproof, evidence-based conclusion.
Part 3. The symptoms, top examiner warnings. Across literally thousands of exam papers analyzed worldwide by Cambridge examiners, there are exactly 3 classic, fatal mistakes that candidates make year after year when tackling 9.1 computational thinking skills and abstraction. 3 specific symptoms that basically guarantee a failing grade on a high-mark question. I want you to think about your own recent mock exams right now, or maybe the feedback your teachers have been giving you all year. What is the one thing that always seems to trip you up? What's your biggest symptom? We are about to reveal the examiner's top 3 warnings to see if you guessed yours right. But first, stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's get into the diagnosis. These 3 symptoms brilliantly illustrate exactly where marks go to die on exam day. Symptom 1, using the wrong formula or algorithm for the specific context. Listen, you might memorize a perfectly efficient sorting algorithm, you might know it backwards and forwards, but if the exam asks you to optimize for a scenario with highly constrained memory, and you apply an algorithm with terrible space complexity, you fail. Context is absolutely everything. Symptom 2, missing boundary conditions and edge cases. You test the normal data, everything looks great, but you completely forget to test what happens when the input is 0, negative, or exactly at the maximum limit. That instantly shows a lack of computational thinking to the examiner. But symptom 3 is the big one, guys, providing generic answers not linked to the scenario. Major examiner alert here. The absolute fastest way to lose marks is giving generic, textbook answers to highly applied questions. Let's do a quick find the flaw challenge. If you write, abstraction is removing details, therefore the system will be faster. Tell me, what's the flaw? The flaw is that it is completely generic. You get 0 marks for that on a scenario question. Now, look at a top candidate's answer. By abstracting the user interface details and focusing only on the back-end transaction processing, the banking system will reduce latency during peak hours. Do you see the difference? Always, always, always link every single point to the given scenario. Now, a lot of you are probably wondering, how on earth do you remember all of this under the intense, ticking clock pressure of a timed exam? I am prescribing a vital technique drawn directly from our highest performing research sources. It's called the visual story method. You need to encode these abstract computer science concepts visually so they become utterly unforgettable. Don't just sit there trying to memorize bullet points from a textbook. Create a vivid visual narrative in your mind. For example, to remember the true essence of abstraction, I want you to picture a massive, incredibly complex jumbo jet. Hold that image in your head. Now, picture the pilot sitting in the cockpit. That pilot does not need to know the exact thermodynamic equations of the jet fuel combusting in the engine, right? They just need to know that pushing the throttle forward makes the plane go faster. That throttle is the abstraction layer. It completely hides the terrifying complexity of the jet engine behind a simple, intuitive interface. When you are sitting in the exam hall and your mind suddenly goes completely blank, don't panic. Recall the visual story. Recall the jumbo jet. Recall the pilot pushing the throttle. The technical definitions will naturally flood back into your memory because human brains are wired for narrative, not for storing raw, isolated data.
Part 4, the clean bill of health, critical analysis.
I want you to actively think about this question for a moment. Really ponder it. Why is evaluating algorithm efficiency so incredibly hard for most students?
Why does it cause so many headaches? I'll tell you exactly why. Because it requires you to hold multiple, often competing variables in your head at the exact same time. It's not just a simple right or wrong, black or white equation. It requires you to balance complex time management matrices, deeply understanding that an algorithm that runs incredibly fast computationally might also consume absolutely massive amounts of memory. It requires a deep, intuitive understanding of trade-offs. The average student, like Sam, sees a working algorithm, sees that it compiles, and says, "Great, it's done, moving on." The top-tier grade A student sees that exact same working algorithm and immediately asks, "Okay, but at what cost?" Let's move to this evaluation table, because it is essentially a cheat sheet for securing maximum marks on those brutal evaluation questions. When you are evaluating a solution, you must explicitly discuss how time complexity interacts with space complexity. You analyze the trade-offs. Let's do a 30-second speed writing challenge in our heads right now. How would you phrase a top-tier evaluation? You might write something like, well, algorithm A offers superior time complexity of big O of n log n. Its space complexity makes it completely unsuitable for the severe memory constraints of the embedded system described in the scenario. Do you see what just happened there? You didn't just state a fact. You acknowledged the limitations of the algorithm, and you justified your final decision with hard evidence extracted directly from the text of the prompt. That is the gold standard of computer science exam writing. You consider multiple potential solutions, you weigh their pros and cons analytically, and you prove beyond a shadow of a doubt to the examiner that your computational thinking skills are advanced, highly nuanced, and directly applied to the problem at hand. And that brings us to the end of our diagnostic clinic. We've established your core principles, implemented a systematic methodology, diagnosed the fatal symptoms holding you back, and provided the ultimate framework for a clean bill of health. Remember the Computer Science Success Blueprint. Rule 1, Command Word Decoding. Rule 2, the PL Framework Application. And Rule 3, the Time Management Matrix. Mastering 9.1 abstraction isn't just about passing a test. It's about fundamentally rewiring how you view complex systems in the real world. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.